This is for dynamics. Chapter 13 homework. I tried to record this on a computer, but it would not take my audio. So I guess we're doing it this way. I'm actually going to work backwards as well, because I solved these problems more recently. So this first one is the block has, so there's a block that's moving, has initial velocity, hits a sphere on a string, and it moves up. And we're trying to calculate the distance that the block slides, as well as the height that the ball reaches. So we have two unknowns. Can already tell this is going to end up having two different equations. So the first one, I basically just solved for the impulse before using the momentum before and after for both the block and the sphere. So I just solved for the impulse, put those together. I know that some of the energy is going to be gone because it's slightly depleted each time, and that's through the value E, which is given to us. So I just plug those in, and I get the velocity B final equals negative 1.6 plus Vs final. So using the conservation of momentum, I get another equation, which is the 2 plus 0.5 Vs plus Vb, and I can actually sub this in for this, solve for the velocity of the sphere final after the collision and everything, plug that back into either one of these equations and get the velocity of the brick final. And then from there, it's just simple kinematics or conservation of energy. So for the sphere, you can just use conservation of energy. Kinetic energy equals mgh. Solve for the h. For the block, you have to use the sum of the forces equals the mass times the acceleration. And we know the acceleration is going to be the 5.866 meters a second, which is from the coefficient of kinetic frictions times gravity, because the sum of the forces is going to equal the mass times the acceleration. So you can solve for x that way using this kinematic equation, which is the Vf final squared equals V naught squared plus 2a delta x. So yeah, that's that one. For this one, this is the symbolic equation. Similar process, you just have to do it a few times. Using the, so since the masses are all the same, you can actually just keep these as velocities, because all the masses would just cancel out. So we have the conservation of momentum right here. So this is the momentum before and after. And then we have the relative velocity equation here. And you can just solve for VB, VA final, plug them into each other, and get these two equations. And then you basically just do that process over again, plugging these back in to solve for the velocity for B and C, the two ones after. So you just take that momentum from B hitting C, and you can calculate the momentum for C that way. And basically it just requires subbing everything in using some creative algebra, and you can actually pull out a 1 plus E, and these would just be times together, give you a squared. So kind of an interesting that the relationship is a square, but that does make sense. So for number 10, this one was the bullet in the block. That's right. So basically we have like a bullet hitting a block, and we're trying to find the initial speed of the bullet. And what we did, okay, gives you all those values. So basically I just used simple conservation of energy here. The initial kinetic energy of the block as soon as it's hit is going to equal the mass times gravity times height. So using that, you can actually solve for the velocity of the block. So that's how fast the block is moving, like as soon as it gets hit. And then using that velocity, you can use the momentum plus the impulse equals momentum final to solve for the impulse itself. And then that impulse is the same between the bullet and the block. So you can actually just go in reverse, but instead use the mass of the bullet to solve for the velocity of the bullet. So that gives you that. And in tension, you're just going to use, net force equals mass times acceleration. Since it's under tension and it's moving in a, circular kind of motion because it's on a string, the tension, the net force, will equal mass times acceleration. The acceleration will actually equal v squared over L since it's in the normal direction. So using that, you can solve for the tension. You have the mass times the gravity, you have the velocity, you have the length and everything. Pretty simple. You can solve for tension that way. So for number 9, this one was the sliding mechanism attached to the pulley. There's like a weight pulling it down. I could have numbered these or labeled these better. I'm still getting better at that. But the P1, P2 is for the sliding mechanism, and the P3, P4 is for the weight on the string pulling down. So one thing to note about this one is the tension. There's 2 tension here, 1 tension here. So in terms of length, this one has twice the length. So that means the velocity of this one will be twice as much because, it has to move the same distance, the rope, but since there's only 1 instead of 2, it's going to move twice as fast. So the final momentum will be the weight times 5 meters a second for the block moving up. The sliding mechanism will be 8 kilograms times 2.5 meters a second. So you can solve for both those momentums and then solve for the impulse in terms of a function of time. So you have the tension and then the time function 1, and then I just do the same for the block on a string. So this one was for the sliding mechanism, this one's for the block on the string. We know the impulse and everything is going to stay the same, so you can actually set those equal and solve for time that way. And then the tension, you can just plug that time value into either one of those equations and solve for the tension. For 8, this one's the truck on the hill. What are we solving for here? The braking force, time required for the truck to stop. So I basically just calculated the momentum of the truck initially, finally. Pretty simple. You can just solve for the impulse that way. So the impulse is the force, net force times the time. And it gives you the time. It says it takes 6 seconds for it to slow down, and we know that it's slowing down, so the momentum is decreasing. So that means this impulse has to be negative because it's taking energy out of the system. So you have gravity pulling down and the braking force. So there's gravity, there's your braking force. You can just solve for the braking force that way pretty easily. And then using that braking force, you can just use the same concept, the conservation of momentum, or the change of momentum through impulses, but now the velocity is 0, so the impulse is 0. For the final, you're going to solve for time by plugging in the braking force and gravity and the initial impulse. So kind of like a kinematic equation in a way. 7, so this is one of the work ones. Been a little bit since I've done these ones. So this was the box sliding on a string, but the spring was already, or sliding down onto a spring, but the spring already has some tension because of some cords holding it back. So basically what that means is for the potential energy of the string, you're gonna have the total amount it moved after the block hits it minus the initial amount. So that's going to give you the total potential energy from the spring after the box hits it, since it's already under tension. So to start, you just solve for the kinetic energy, the change in momentum from moving position. So it's in the direction of motion, so this is going to be positive. And then you can just use the conservation of energy to solve for the change in distance. So we have all these numbers. This is the kinetic energy to start. That's the work done from it moving position. And then we have the spring potential energy. Sorry, that's supposed to be a V. Anyways, and then we have the potential energy of the string minus the change in position there. So pretty simple. So this one was the spring on, like the collar sliding around like that. And it's not circular, it's kind of more elliptical. So basically what I did is I just calculated the energy at every point. So we have the energy at point A. Well, this one, it has no MGH because it's, not moving any position relative to C. I just use C as like the baseline. So no movement, so there's going to be no work done from it moving position. The only energy is from the spring itself. So basically you can calculate total energy that way. For that one, for B, same thing. This one is going to have some work done because it's moving downwards relative to A and C. So you can calculate the velocity of B at that point, just using conservation of energy. Same thing at C, and we know at C there's the spring is, the X is 0, so there's no force from the spring, so it's all just the kinetic energy. So you can solve for the velocity that way, since it's always going to equal 3 joules anywhere you go. So yeah, that's that one. For 5, this is the ski lift one. Definitely overcomplicated this one to start, but pretty simple. So we're trying to calculate the average power, which is in watts, because watts is like joule seconds, I believe, joules per second, which is what we're looking for. So pretty much I just used the change in potential energy. It's moving all this mass up the hill, and there's going to be a total amount of energy required to move that, much mass up the hill. So you can actually calculate the total amount of energy needed to move that many skiers up a hill in 1 hour in joules per hour. And then you can just convert this to joules per second, which gives you watts. And then for the 300% overload, you basically just need 300% extra. So I have the 100%, which is how much we currently need, and then the 300% extra gives you that much watts. And then the motor is 85% efficient, so only 85% of the power going to the ski lift actually goes to moving the skiers up the hill. So you just divide that by, so let me word it this way. So the power going in equals 0.85 of the power actually going to moving the skiers up the hill. So you can just solve for that power, 269,000 watts or 269 kilowatts. So for 3, so this is the one where they ball on a string, they push it down, and we're trying to find, oh wait, did I miss one? Worked on my ski lift. Okay, yeah, that's this one right here. So 4, this is the one on the string, and the guy pushes it down, and we're trying to find when it snaps if we know that the tension can only withstand, twice the maximum weight of the sphere. So I just calculated the kinetic energy initial, kinetic energy final, because it's moving in both instances, so it's going to have kinetic energy at both. But I just calculated the work done from the movement. So from it moving to, from here to some point down here, whatever that point may be, there's going to be work pulled in or taken out of the system. So, and that's at the final part. There's no initial, the change has to be negative, is what I'm saying, because it's when you add it to this side. That's what I did. Sorry, I confused myself. So this is supposed to be positive because work is being put into the system. It's going the same direction as the ball's moving. It's moving down. So ultimately, we have the kinetic energy, the work done from it moving position, which is the gravity times the length times sine theta. And that's what we're ultimately trying to calculate, is where this angle, the weight of the ball essentially feels double on the string, equals the velocity final. So you can use that equation, solve for, in this case, I solve for the velocity final, but we still have the unknown theta in there. So basically what I did is I did it again in the, I used the tangential coordinate plane here, the normal tangential, because it's a ball on a string. So I use the acceleration is going to equal the velocity squared over the length of the rope. You can leverage that, use Newton's law, where the net force is going to equal the mass times the acceleration. So the net force is going to be the tension, and then this mg, whichever direction, goes in the opposite direction of t. So we have the tension, and then we have the gravity that's in that same direction, or opposite direction, I should say. So we're going to subtract those to get the net force. It's going to equal the mass times velocity squared over 2, using that acceleration in the normal direction. Gives us another equation, and you can actually just sub these in, because this is velocity squared as well. Velocity squared, set those equal, solve for the sine theta, should give you close to 14 degrees. So for 3, this one is the train car one. This was a good problem. So basically, how I solved this one is I did it for the entire train. First, all the masses put together, using just the normal force from the initial car, because the only car braking is car A, right? So the force from friction is going to be the normal force of just car A times the coefficient of static friction. If all of these were braking, then you would use the normal force for all of the cars. You just use it as like a point mass if you want. So we have the initial velocity of everything. It's going to a complete stop. Really, the only thing is just the change in position. Or I'm sorry, that's the potential energy. No, what is that? So that's the change of work done from it moving from one place to another, which equals the force times the distance. Yes, okay. So that's just the change, the work done from the friction on the track times the distance. And ultimately what we're trying to solve for is the distance. So we pretty much can just set these equal. So we have the initial kinetic energy is going to equal the work done from the brakes, and everything. So you can solve for the distance that way pretty easily. And then leveraging the distance you just solved for, you can actually solve for the force in each coupling because there's no braking force on the rest of the cars. So the only net force acting on each car is the force on the coupling that's pulling it, right? There's no like engine or there's no friction stopping it. So you can solve for the force of the coupling because we know how long it takes to come to a complete stop. And we know the initial velocity. The mass is slightly different because this is the mass of the two cars being pulled, not including car A. And then for the last one, it's just the last car because we're trying to solve for the force in that coupling between B and C. So yeah, you can just use the different masses, leveraging the distance and everything, and how fast it's going to solve for the force in each of those. So for 2, this is the truck going up a slight incline. We're solving for the average force of the wheels and the average force in the coupling between the cab and the trailer. So similar concept to the train car one. For part B, we're going to use just, I guess I'm jumping ahead here. So I guess we'll start with solving for the force of the engine, I guess the wheels on the ground, moving it forward.